This is Ship It with Justin Garrison and Autumn Nash, a podcast about everything that happens after Git Push. Ship It is brought to you by Fly.io, the home of changelog.com. Launch your apps close to your users all around the world. Learn how at Fly.io.
Hello and welcome to Ship It, the podcast all about what happens after you Git push. I am your host, Justin Garrison, and with me as always, Autumn Nash. How's it going, Autumn?
Good. Also, I feel like the last 20% of all software projects and then the maintaining it part is almost more painful than the beginning part.
The life cycle, 80% of software is not the writing of the code, right? Like that's
Nobody tells you that in college.
We cover most of software on this podcast if we want to just group that in the 80% of the life cycle of software.
The part where the struggle gets real.
This is where you cry. This is the episode where...
Okay, can we talk about that? Why are all the memes and TikTok videos and Instagram videos, they're like, I'm a software engineer, and then they're crying? Like, I'm like, there is a pattern. like, no one told me that, like, 50 to 75% of this job would involve crying at your desk and then like asking like the computer and like compiler gods to like fix your life.
A lot of the memes are like writing code is hard, right? Like figuring out that algorithm or that loop or the clever way to do something is the hard part.
That's the fun part.
Right, you got to figure out a problem and you're like figuring it out on your own time.
And then the edge case ruins your entire life.
When software interrupts your life.
Just kidding. Yeah. Like, let's stop lying to people, okay? Like, we just want you to know it's real fun, but you may cry.
It does happen sometimes.
There will be tears, like, just saying.
On today's episode, we have John Johnson, who's going to talk all about TARs and compression.
His excitement for TARs just makes my heart happy.
Oh my gosh, the plus content on this episode is the best.
That is the cutest poem I've, and it's like, can we just, he dads hard, and we know how he dads hard because the way that he like read it was like perfect storybook nighttime dadding, and the way that he made it like rhyme, like fire.
He's read some Dr. Seuss in his
right?
life, that's for sure.
Like, he's the Dr. Seuss of TARs. Like, look, whoever did Deflate needs to call them and like write that poem into their documentation. Okay, like just a little video snippet of him.
Yes, if you want an episode with links to RFCs and also poems, this is the episode for you.
Like, okay, but how wild is that? Like, that's why I love tech. Like, people get so, like, it's just, like, all of us, like, in our, like, random nerd hyperfixation about, like, what you just, like, really love, and seeing people's eyes light up and they get all excited, it just makes me happy on the inside.
Yes, it is great. To start the episode, before the interview, we're going to go ahead and go into a couple links for this week. And Autumn, I'm going to have you go first this time. What do you got?
Okay, so I'm reading all the tweets from Microsoft Build, which I think are actually pretty exciting. Like, it's really cool to see the new Snapdragon chip.
Yeah, the new Qualcomm Snapdragon X. I want one of those as soon as I find like a desktop or a dev reference board. I don't want a laptop. I want an actual, just like stick it in a corner and run with my home lab.
I know. I'm like, the way that you love like Linux, I can't imagine you buying like a straight Windows computer, but I do want to see what you do with that like chip. But it's interesting because they're saying that the Snapdragon was created to basically filter all of the AI like data that it's going to take off of your laptop. So basically these laptops are going to constantly be viewing what you're viewing and like collecting data to help you search. Right. But like then you get into data privacy. Like, is that FedRAMP and HIPAA compliant if like it's constantly looking at what you're doing and your bank account numbers and your medical and health? You know what I mean?
Anything on your computer.
Yeah. Like, I mean, I think there's some stuff that like we don't need to know about every nerdy Google search that I do, you know, like, like we don't need to know my full shopping history because that I like at 11 o'clock at night. Like, but some ways data collection can be really helpful. We all love when like the algorithm tells you about this really cool thing you didn't know about so you can buy it. But it's interesting. Is this going to be the new way that we do it, where you can take in all this information because a chip is going to filter out how to process that away from your other information? I don't know. I'm excited to see where the things that AI helps us do to like make it where we can be more efficient to do things that we want. But I feel like we're getting in this weird
like, collect all the things.
Yes. And it's like, is this spyware or is this better? Like, it's getting weird. Not just that, but the lady from Bumble said she wanted, instead of us doing like dating, she wants us to basically have 2 AI secretaries talk to each other. And I'm like, yo, like, I thought AI was going to do all the stuff we didn't want to do. Like, why are we giving it art and music and writing? And like,
you've seen plenty of people on dating apps. They don't want to talk to people either. Like,
okay.
Social anxiety is real.
My dating history, like, it's been rough. Like, I think I might need therapy from dating, like, at this point. But
there's an AI bot for that.
I don't know if it's going to get better. You know what I mean? Like, it will just be like even more like fakeness.
2 people show up in real world. They're like, oh, so, or bots talk to each other, right?
That's like, I don't know if that makes it better. Like, you're just sitting there like, it's like there's so much fake stuff that we already have to present this version of us on social media or on dating apps, and it like doesn't that make a layer more of trying to figure out who's the creeper or not? Because they won't like the AI might like make you think they're normal and then they're like secretly super creepy. Like, I don't know.
Yeah, it's going to be really weird. I don't know. There's just we're putting in everything because it's making money, and that's like right now this announcement with Copilot and Microsoft's whatever the new Windows feature is that's making Copilot Plus.
Which Copilot, regular Copilot and an IDE is really good. This is like, I don't know.
Well, and that's GitHub Copilot, right? Because there's like Copilot is also the Microsoft branded thing, which is just generic, like the Bing chat side of things. That's not coding, but there's GitHub Copilot, there's Bing Copilot. This is like the PC plus Copilot thing.
They're kind of naming everything Copilot, which makes it hard to differentiate what.
They went hard on that naming, and now it's really hard to figure out which one's which.
Yeah. I love using like ChatGPT and different like AI as like the rubber ducky to get out your ideas. I feel like it's made me so much faster of a writer for like different talks and things, just because you can be like, okay, I have all these ideas. What's interesting? What's already been done about it? Like, where would you start an outline? And then like I get over that writing block of being able to fill in like, okay, this is like, give me like a template to fill in type of deal. But this is like, we're almost taking the fun out of everything. I don't want it to create content for me. I want it to catch my spelling errors and like help me make it sound better. Not like you're taking all the fun.
Well, I mean, like I have spell check in my Vim without an AI bot, right? Like those are things that like a known dictionary of words also works.
But I do think that at some point we can make it better, like just regular things that we have, but we can make it better, more efficient with like technology. But this is like, I don't know where we're going with this.
To me, one of the best things about using a chatbot or AI in some way is the hallucinations, the actual extreme sides of things where it's like, that's to like, no, for real. It's like, I'll use, ChatGPT or Midjourney, all of the other bots. Like, I'm like, hey, do something along these lines. But then I try to trip it up enough to get something outside of what I would normally think of, just to help me think of something else. And that's
kind of what I'm saying, but maybe not to that extreme. But like it helps you, not just that, but sometimes things can get so repetitive, and being able to like quickly search like what's out there, what is like the coolest, most off the wall ways to do this, you know what I mean? Or like the different perspectives. But I do think that like I love talking to you about different perspectives on stuff, because I feel like you always have the Justin approach to something that I've never tried before.
I guess most AI, right? If you're an expert on something, you're going to be smarter than the AI is for just like general knowing things. But to like summarize something else, and for me, like thinking outside of the box, like, hey, I want to think of this in a different approach.
I also like it as a fun way to learn. Sometimes you can only read so much, and you can only like watch so many videos. Sometimes having that back and forth conversational like approach like to learning a new subject, and then you can ask questions, and then you're like, okay, I get this and this now, let's go deeper on this, like using it as like almost a way to have a conversation to learn. I really enjoy that.
You're just being able to direct your interests, right? Because you're like, oh, that sentence was interesting, that one wasn't, so that one, like, and then just like, let's dive into this piece of it. And I do think that there is some value in like PDF summarizations and white papers and those sorts of things. Are like,
and having somebody sort of explain something back to you is a different way of learning than reading it, right? Because you can ask questions when you're confused somewhere, but then it's also like, there's also a lot of times where I've gotten that and it's been the wrong question. So I don't know.
Yeah. Well, and so what was Google recently had their developer conference. Microsoft Builds is having their dev conference. Both of them all about AI. Apple's, I think, is next month.
Yeah, they're next.
It's all going to be AI, I'm sure. So for anyone that wants to jump on Linux on the desktop, hit me up.
Yo, half of Twitter is like, if Apple goes in hard, where's Linux? And I'm like, and then somebody was like, Linux had 200 CVEs, and I was like,
that is less than every other OS.
Like, I don't know if you're making a case. Like, I think the case that you think you're making, you're not making.
Yeah. So yeah, it's been interesting. My article is similar, and in that it's about Microsoft and AI, and this one specifically calling out that Microsoft's AI obsession is jeopardizing its climate ambitions.
I think this is really interesting, and I don't think we should just dog out Microsoft on this one, because this is everybody. When it comes to a data center, you're either picking between using a ton of water or a ton of electricity. You know what I mean? And this is going to be everybody. We were talking so much about wanting to fight climate change, and AI is like, we've completely gone backwards on all of the goals.
Yeah, and I think this one specifically this article is calling out Microsoft because in 2020 they said they were going to be carbon neutral by the end of the decade, and in the last year they increased their carbon outputs by a lot because of the new data centers and AI training, because AI training and GPUs consume a lot more power than traditional web workloads and whatever we were doing before. And so I also wanted to call it, this is kind of ridiculous. They have a sustainability report Microsoft puts out that this article is referencing. It is 88 pages of complete marketing nonsense. And I'm thankful for whoever it was at The Verge who went through this and found the differences of like, oh, this was hidden somewhere in these thousands of words. Maybe AI pulled it out for them. I have no idea. But
I just want to thank tech reporters, because sometimes they at least tell you where to go look. So then you know that you know what you're getting yourself into, but you know what you're looking for. You know, like you can go back and check their sources, but at least they tell you what's up.
And this was one thing, like I like to look at sources a lot. And so I opened up these sources and I was like, there's no way that you could decipher what this one says compared to the one they said from 3 years ago.
But see, this is why I don't understand how people are so all in on any source that is just kind of giving you like answers for something. We double check like our sources on Google. When you were in college, could you just submit any link that you wanted? No. Like, you know what I mean? You had to like verify your sources. We don't let news reporters do that. We don't just take their word. So the fact that they're willing to just take AI's word, it's not even like AI is bad. It's just that you should always check your sources and make sure you're learning stuff. And the fact that we're just like willy-nilly giving them control over everything, and you're like, but this is a terrible idea. We don't even do that with humans.
It's a non-determinate system, right? Like when we're trusting this big blob of information that gets spit out some way, and it's the same thing for humans, right? Like there's biases and there's things that happen over time, and
us humans are honestly going to mess up AI. Even if it had a chance of being great, we're going to put biased data into it because we are biased, you know what I mean? So there's always has to be like, you can't just trust one human, you can't just trust AI. It's got to be checks and balances for everything.
But I mean, specifically for my article, I just found it interesting that, you know, 4 years ago, when your stock price would go up by being carbon neutral, that's what Microsoft did. 4 years later, when AI will make your stock price go up, that's what Microsoft did. And I feel like company over company is just chasing the stock price, and it is very dangerous.
First, it's the carbon neutral. It's also like people were like, we should hire people that are like diverse perspectives, and now they're like, screw your perspectives. So I feel like we are on that in a lot of areas right now. Tech is getting weird.
Yeah, there is a lot of, especially in big tech, I feel like a lot of just chasing the stock price and doing whatever is going to drive that price, because that is the ultimate thing.
Which kind of sucks, because we were building some cool stuff, and so much cool stuff just kind of like, I mean, there are people, of course, still building cool stuff, but it's just like, it seems like we're just doing the same thing over and over, and it's hard to get excited like we used to. Like, you know, there was like cool, I don't know, Snapdragon's pretty exciting, but it's hard to get excited. Like all these different conferences, like you would be like, oh, did you see this new thing? And I totally want this, you know, and like it would be like, I can't wait to try this out. And now it's like the same flavor over. And I mean, to a certain extent, there's always a trend, but this is like I think we've already found the cool things to do with it. And of course, there's going to be like other cool things, but I'm just like,
There's a lot that might shake out still, but it's definitely not bubbling up to the surface. And the mainstream stuff is not what I'm asking for. Right? It's not what a lot of people are asking for.
yeah, because I'm like, dude, there's so many cool things that I feel like we haven't even scratched the surface on or really like looked into.
So with that depressing news, let's jump into the interview with John.
We could be more depressing. We could talk about the market.
let's just sidestep all that. We're gonna talk about TARS. We're gonna talk about deflate, and we're gonna learn a lot about just how
that
basically
TARS cheer
TARS.
me up.
All of this TARS rule the worlds, and really, like if you think AIs are taking over, like really, like TARS is the OG. Like they were here before AI.
This is also a great example of when a developer is interested in something, their natural curiosity will go through the ends of the earth to find a good solution. It is the best. It's like, this is the epitome of software development right here, like the warm and fuzzies.
So let's jump to that interview and we will talk to you again after.
What's up, friends? This episode is brought to you by our friends at Neon. Managed serverless Postgres is exciting. We're excited. We think it's the future. And I'm here with Nikita Shamganov, co-founder and CEO of Neon. So Nikita, what is it like to be building the future?
Well, I have a flurry of feelings about it, coming from the fact that I have been at it for a while. There's more confidence in terms of what the North Star is. And there is a lot more excitement because I truly believe that this is what's going to be the future, and that future needs to be built, and it's very exciting to build the future. And I think this is an opportunity for this moment in time. We have just the technology for it, and the urgency is required to be able to seize on that opportunity.
So we're obviously pretty excited about Neon and Postgres and managed Postgres and serverless Postgres and data branching and all the fun stuff. And it's one thing to be building for the future, and it's another to actually have the response from the community. What's been going on? What's the reaction like?
We are lately onboarding close to 2,500 databases a day. That's more than one database a minute of somebody in the world coming to Neon, either directly or through the help of our partners. And they're able to experience what it feels like to program against database that looks like a URL, and the program against a database that can support branching and be like a good buddy for you in the software development lifecycle. So that's exciting. And while that's exciting, the urgency at Neon is unparalleled.
There you go. If you want to experience the future, go to neon.tech. On-demand scalability, bottomless storage, database branching, everything you want for the Postgres of the future. Once again, neon.tech.
All right, welcome to the show today, John Johnson. Thanks for joining. Tell us a little about yourself.
Hi.
We're gonna stop laughing at some point.
For anyone that's just joining this conversation, we've been talking for like a half hour now, and it's been a great conversation before the show. So we're just going to carry this right into the podcast.
Like, I'm at 2 cups of coffee and I still can't focus. Like ADHD. Like, we're just going to be here for like.
Does coffee help you focus? I don't think so.
It does.
You need some tea, maybe.
Some tea. There you go. See, John's dropping.
Don't be on his side.
So John, tell what do you do?
Yes. What do? I do container things at ChainGuard. In a previous life, I did a lot of container things at Google, but that entails, say, building, debugging, publishing, serving, etc. of containers and all of our various container tools.
What software are you responsible for?
A lot. So I am responsible for the ChainGuard registry at cgr.dev and our build tooling, both AppCo and Melange. I'm responsible for Go container registry stuff and the Google library, and also the Crane CLI that is derived from Go container registry. I'm responsible for the Co build tool for building Go containers, and probably more things I can't remember, but would sound very similar to that.
I feel that.
If it has Go in it, if it has container in it, John's probably touched it.
I have touched most container Go things. Yes, I think even if you talk about Containerd, Docker, or even the Red Hat ecosystem of container tooling, I think my name's somewhere in that commit log somewhere.
And when you reached out, we were talking about being on you coming on the show. It was like you were talking about tars, right? Like it's just like
yes,
the container is it's a 3 tars and a trench coat, and that's it.
Earlier today, I was coming up with jokes for the show, and I thought I had come up with that. Like I was like, oh, I'm going to say it's like 3 gzips and a trench coat, and then I opened this. I was like, oh, Justin made this joke already to me, and I was devastated.
It's collaborative. It's fine. I'm pretty sure you probably said something along those lines in the email, so we're good.
So you guys work on your dad jokes ahead of time? You don't just come with them?
These are planned. Oh yeah.
I feel like I've been lied to. Like it's like you just told me Santa's real. Like those like dad jokes don't just like live.
I mean, but my second joke was a mistake, so unplanned.
Oh my goodness.
You practice. And then they come out naturally.
You're waiting for the moment. Like you have a backlog and you're just like, oh, is now the time? And you're like, no, not at the funeral. That's not the time.
My kids have like started telling like dad jokes and I'm like, you're too young for this. Stop it. Like
you got to start them early.
So about tars and gzips, like explain to us. I mean, you've been doing so much stuff with registries and you're either packing or unpacking gzips over and over again in pretty much every situation, right?
Yes. I have a small confession to make, is that I'm here mostly because of the episode you had with Jason, and I want to correct the record on something he said.
Oh, okay. Here we go.
So first of all, I was very excited that he was coming on the podcast because he's way more eloquent than I am and has a lot of more interesting things to say. But when I listened to it, I was devastated that when you asked him if there were any surprises for moving to Terraform, that he totally didn't mention anything that I had been working on because I was so excited about it. And I accused him of this. I was like, Jason, surely the stuff I was working on is interesting. He's like, I did. I swear I talked about it. I mentioned it. It's like, I don't know.
Did you side-eye him in like your next one-on-one and you were just like,
no, I gave y'all $10. Like, so it made it into the Changelog plus like bonus content at the end where I get name dropped. And so I was like, oh, so now like I've been baited into being a Changelog plus subscriber.
We will mention your name. Anyone that wants to send $10.
Right.
I love how out of vanity he was like, look, I'm gonna find my name in here somewhere. Like,
right. Surely. So he, he said, no, I did talk about it. So I got into it. I was very excited. I paid $10 to listen to someone talk about me. And then he missed the numbers. So like flashback to Changelog plus content, I guess, is that Jason made this claim that we were spending something like 30% of our time marshalling Jason, which was a huge waste of time. And I was like, no, Jason, we were spending 30% of our time just indenting it. We were actually spending 75% of our time marshalling it.
Good Lord.
Yeah, the reason I remember this so distinctly is that once I had figured this out, our GitHub Actions, which were timing out after an hour, took 15 minutes. And so we were spending 3/4 of the time just marshalling and unmarshalling Jason.
Someone at Hashi, like, get this on a commercial or like a testimonial for your next talk somewhere.
Right?
So wait. So originally you were sending these giant JSON blobs in and out of packaging container, right? Like, is that where the JSON was coming from? Where was this coming from?
No. So this was just Terraform state files. Okay. And so basically every state transition incurred serializing the entire state and then like diffing it and then saving that. And then the next step would load it from disk. And so our state files were like tens of megabytes at that point. And
that's a big state file.
That's also a lot of overhead cost of storing all it.
Yeah. Well, you end up throwing it away immediately.
Yeah. It's ephemeral.
Right. So what is funny is that I did all this work to like figure that out.
He's making the Justin face. What are you thinking?
No, go. I'm just listening. I'm trying to think of like
his face was the best. I was like, oh no, something's in there.
So I spent weeks basically figuring this out and figuring out how to fix this. And I found a bunch of to-dos in like the Terraform code base about this. And I to-did them. And then
to-did
them. I'm using that.
The git commit right there. To-did right. All of the to-dos.
This was in the middle of kind of the drama around Terraform relicensing stuff. And so I ended up like sending a PR to Open Tofu. I think it was called something else at the time, but I sent them a PR. And I was like, cool, we just have to wait for them to release it. And then that took a while. So I ended up actually stumbling upon the solution we went with, which was like this nmem state store that just throws it away anyway. And so we didn't even end up using this work I did for like 2 weeks to fix this problem because I found a workaround. But it is in OpenTofu now. So you should not run into these problems if you end up building several thousand containers with Terraform with state marshaling. So
Playing it forward.
yes.
As you just pointed out, there's multiple ways to fix that problem, right? Essentially, you can make the marshaling unmarshaling faster or better, or you can just like speed up your disk. Essentially, of like to put it in memory, right? Like make it the fastest disk possible, and just say it's going to be in memory. What other benefit? Like, could you do this in a different language that is better at marshaling? Like, if Terraform wasn't in Go, and we were doing it in another language that had better JSON handling, would that also?
Is Terraform written in Go?
It is, yes. I think probably because you may be familiar with the fact that the JSON package in the standard library is going through a V2 design phase right now. But there's not like any way to do random access of stuff with JSON in Go. And so I think if you had something like this, you might end up with people writing code that took advantage of it. But like, obviously from Terraform's perspective, it's like, oh, writing JSON to disk is really like fast relative to all these like expensive infrastructure operations. So like, we're not going to pay attention to that, right. That should be the fastest part of this whole operation. But when you do it, say 30,000 times, ends up slowing you down quite a bit.
And I remember a long time ago, there was a service that they did a comparison between, they were rewriting it from probably Scala or something. And they're like, oh, we want to rewrite it. And they were like, we're going to go with Go because it's fast, right? And it's like, oh, we can compile it, it's fast, everything. And then a comparison with a Go version of the service and a Kotlin version of the service. And it was a GraphQL API. And they're like, actually, Kotlin was a lot faster just because we had to keep marshaling and unmarshaling JSON over and over again. And there's like, actually just the handling that Java and Kotlin gave us was faster than Go. And it's like, that was an eye opener for me because I was just all in on Go must be fast, right? It's like, well,
I'm just happy we're talking about Java right now.
I autumn was coming about. It's like, I know there's going to be, because like Java is really good at handling JSON, and it's like you can,
and it has gotten considerably faster. Just want to drop that.
But again, like back to that, how do you solve this problem? Is like just having the fastest disk possible is.
Also, I think it's interesting just to point out that it's funny that there's so many ways to solve the same problems in tech, and there's so many different tools that are made to do it. And then sometimes it's still the legacy thing that we've had for 40 years. Even though everybody wants to do the hippest new like Go and Rust. And sometimes I'm like, Java could work for this and we could save so much time. You don't have to reteach like a whole team of engineers to write Rust. We could just do it in Java.
But then how are they going to put that on a resume? That's
You're not wrong. Somebody wants to write some sort of doc to propose it somewhere. But
So setting the record straight.
Yes. Apologies for the digression.
No,
but it also, I think, is relevant kind of to the rest of this. So I got into thinking about gzip deeply for a lot of reasons, but one of them is performance, right?
So it's when you go down that rabbit hole, when you start Googling stuff and like looking at 8 different projects and you're like 3 hours later.
Yeah. So
that's my life. I feel you.
Yeah. I know that I'm doing like real interesting work when I'm reading RFC in the text format. Yeah. And it's like, okay, I feel like maybe software engineer isn't a made up term. I feel like this is actual work. But RFC 1951, it's a good one. That's
highly recommend.
Put it in the show notes.
Really. I don't know. Should I take you back to like why I started caring about gzip at all, or should we segue through containers?
I'm just sad that the like podcast people can't see the faces that have been made in this emotional roller coaster of like Terraform. Justin has made several great faces. John has made some great faces, and I'm just sad that they are being lost on the audience right now.
Well, we can make some shorts.
Yeah, they'll show up somewhere. But so yeah, like start with what are you doing with gzips? Like, why was this important to solve the next problem?
Sure. Okay, so there are 2 places in my life where my caring about gzip is actually useful and not just some weird thing that happened to me. Going back to 3 tars in a trench coat. I don't know if like how you came up with that. Surely I didn't, but it's obscenely accurate as a description. So before I joined ChainGuard, I had spent about a year just kind of being nerd sniped by gzip in general for other reasons we'll get to. But when I joined, I learned that I would have to do a lot of things with APKs, and I didn't know what an APK was. It's a package format. I believe APK stands for Alpine Package Keeper.
Mm-hmm.
But what I learned is that it is 3 gzipped tarballs in a trench coat. And so
He's not wrong.
yeah, it was surprising to me that like all of the stuff I had learned about gzip and tarballs for container reasons is like directly applicable to now my day job. And so I kind of double dipped on this like weird obsession that I have, which is very useful for a lot of reasons. But for the purposes of performance, it is really useful to us that APKs are just gzipped tarballs, because if you think about how we build a container image with AppCo, right? A container image is also just a gzipped tarball plus some JSON stitched into a DAG. But the gzip tarball bits are like the same as the inputs of APK or as the APK. So you have a bunch of packages. You want to put them in a container image. It's actually really straightforward to turn gzipped tarballs into another gzipped tarball without going through disk in the middle. So when I was tasked with this performance work on our image release process, the first thing I did was look at the AppCo tool. I was like, what are we doing? Where are we spending our time? And I learned that the majority of it ended up being writing hundreds of files to disk and then immediately reading hundreds of files from disk and putting them in a gzip tarball when they had originally been a gzip tarball. And so lots of optimizing, lots of profiling, down to the path where it's like, okay, we don't write every single file out to disk anymore. And it's way, way faster. So the build I was using as a test case went from like 30 seconds to like 2 seconds. And that was huge for our build times. It turns out it didn't help our build times at all because we were just marshalling and unmarshalling JSON the whole time. But once I fixed that bottleneck, it dropped down tremendously, right? And it was like 4 times faster overall. I don't know why we're talking about this anymore. But yeah, this kind of like insight of, oh, like there's actually something here with gzip and performance is why I wanted to talk to you, because it's like, other people should know. This is interesting, actually. Like I care about it. You should too.
One of the things I wanted to talk about too was about like we take all these gzips and whatever we want, APKs or containers, whatever we want to call them, and then we put them in on a website. And we call that a registry or a repo or something that is just a form of a collection of tars or gzips with some metadata on which ones to download when, right? That's like basically the whole thing.
Yes.
Except for I guess Yum packages, which would be CPIOs, right? Those are.
I actually don't know what that format is. And
It's
I
old.
come across it, right? It was like
Yeah.
It looks almost like tar, but it's not. I don't
It
understand.
was before tar. Yeah, no, it was like CPIOs are very ancient, and they run all of Yum.
Terrifying.
But so yeah, we have all these things, and then we throw them in websites, and then everyone downloads them from there. And we say like, okay, we have a website. You can download all the tars you want. Here's how you discover which tar you want. Either that's an APK file for installing a package, or layers of containers, and those layers are broken up into other things and referenced by other JSON files, right? So like my container image is a collection of other tars. What work have you done on that side? Because I think that distribution side of it, like we can package it performantly and then distribute it. And then as people are downloading it, like usually it's like, oh, we make them small. It's like, well, that's not the only way.
Right. So my introduction, I think, to all of this gzip nonsense was StarGZ. So a while ago, I don't know how long ago, but Brad Fitzpatrick, who was at Google at the time working on the Go build system, trying to make the Go builds faster, ran into the reality that pooling was really slow. So they had packaged up in their like Go base images for testing like many, many gigabytes. I think tens or hundreds of gigabytes of stuff, very little of which was actually accessed on each build. So he came up with this thing, which he called CRFS, which is Container Registry File System, that used like a fuse to mount effectively your container image from the registry onto your local file system. And it would give you the ability to access the files directly instead of having to first pull them. But it required pre-processing those images a little bit to be like amenable to this mounting format. So what he ended up doing is effectively rewriting those container image layers to be more like a zip file instead of a gzipped tarball, which maybe is a good digression to talk about the difference.
Yeah. Why would that be a benefit?
So zip files are essentially a bunch of individually compressed files. And then at the end, there is a directory for those files. So when you open a zip file, if you want to look at the contents, your software is going to seek to the end of the file, find an offset that says like how far back to seek. It's going to seek back to the start of a directory, and then within the directory has offsets to all the other files in the zip file. So it gives you the ability to seek quickly to any of the individual files that are contained in the overall zip file. Does that make sense?
I have an index. It's like if I have a book and I want to find the chapter, I can go to the index, I can find the chapter, and I'm like, I can just jump right there and we can get the thing that I wanted.
Exactly. Let's contrast that. So tar gzs are a tar file, which is just a concatenation of all the files with metadata in between them. And there's no index at the end. So if you want to access a file in a tar file, you have to read through the entire thing until you find the file you're looking for, and then you can read it.
So that's why the zip files are faster.
Yeah, there's no index on that. Yeah, okay.
Exactly. So the benefit of tar gz or zip is that gzip compresses like the entire stream all at once, whereas zip compresses each file individually. And so with gzipped tarballs, if you have a bunch of files that are really similar and fairly small, then you're going to end up being able to compress that way smaller than if you had compressed each file individually, like with zip files.
But do you still get the indexing?
You don't, unless you use Brad Fitzpatrick's crazy invention that he called star gz, which is a seekable tar gz file.
So you've got the compression of the tar file, but you've got the indexing of the zip file. So it's not only faster and compressing better, but then it's indexing to find stuff but easier.
Right. It kind of strikes a middle balance between the two. So the way that works briefly is that when you're going through the star gz file, every so often you just like stop the gzip stream and reset it. So instead of being one giant gzip archive, it's actually several gzip archives just concatenated together.
So you're just like chunking like a certain, so you're not getting as good a compression, but much faster read time, because you're like, hey, this first meg is compressed, but then I get some metadata to say what's in the next meg.
Right. So like I think it's every 2 or 4 or something, maybe it's every file, honestly, but every so often you just reset that stream. And then at the end of this stream, you have a table of contents index thing that is, hey, here's all the offsets of all the files I just wrote. You write that file to the tar gz, and then at the very end, you include, here's the offset to that table of contents. And it's essentially identical to like a zip file. It's just in tar gz like clothes, right? So
because you're not getting as good a compression as compressing the entire stream, but you get that faster read time.
But you're basically meeting in the middle between performance and read time, which is like a balance that is hard to strike. So that's like really very functional.
Yeah, it was super, super clever, right? And what I learned from that is that, like gzip is kind of this interesting format where you can have multiple gzips just concatenated together, and gzip decoders are cool with that, right? They're like, oh, that's fine. Like I will just keep reading through. Now that I found a new gzip archive, I'll just keep going and keep decoding.
And one thing that, I mean, I didn't know this for a very, very long time. Like when you say concatenate together, you literally mean like I can use the cat command with 2 gzip files and I can pipe it to another file. And that is literally just, you just append the 2 things together and the cat command will just like, it's one file now. And that's how that works.
Yeah, it's really bizarre, but it works. And so I was very excited about this, right? Because it's like, oh, great, we can get lazy access container images. Everyone should adopt this. Let's do it. And some folks kind of took that and ran with it. And there's another format called e-star-gz, which is basically the same, but if I understand correctly, they have some metadata around like optimizing access patterns. So you can prioritize certain files to like be prefetchable so that you can speed up the startup time even further.
That is really smart.
I no longer am championing star-gz because I learned more things And I think there's a better option.
I love the rabbit hole that you went through. Like, we've gone down an emotional roller coaster of like files, and I love it.
This GZ roller coaster is
Yeah.
taking us for a ride.
It has been like a 2 or 3 year journey for me, which is like just so lame. But I just can't get away from it. And every time I try to, I find out a new thing that I find interesting.
That's when you know you're doing good work, though. Like, a work that's interesting to you is when the rabbit holes, like, that's when you are on the right project.
Right. It keeps going. Right? It's like, okay, yeah, there must be something here. So drawbacks to that, right? As you mentioned, is it doesn't compress quite as well as say a zip file would. Right. You also now have in your gzip archive this table of contents. So when you decompress that container image, there's a weird file, right, in the file system. That's like, what is this? What's this giant JSON
bonus
file? Right? And so that's like the in-band stuff, not great. The other thing is that it doesn't work for existing container images. You have to rebuild with like this special tool that processes the layers to put them in this format, right?
And yet, like, just to give the listeners, like, this was specifically designed for containers for speeding up that pull process, right? Because usually you're going through and you're like, I have a container image, and that's sending you a metadata list of like, here's 10 other gzips you have to download. And with StarGZ, or at least with extended StarGZ, like, you can say, hey, I need to start this Nginx container. So just give me the layer that has the binary Nginx and whatever libraries it needs. All the other cruft in the container, I don't need right away, right? Like, I can load that after the fact. We're still going to download it, but I can start my container faster. And that's a big win when you have tens of gigs in a container. And you're like, actually, this container is really large, and the download takes a long time. Because usually it's just like download, decompress, start. And you're like, hey, let me just download the bits I need first. We'll decompress that. We'll start it. And this StarGZ allows you to optimize, hey, I'm going to rebuild my container and say, like, we're going to profile it basically and say, which files are accessed first? Let's put those in their own layer. And then when I tell you to download this, you're just going to fetch that one piece. And we're still going to download the stuff in the background, but the piece to start will come down a lot faster than waiting for 10 gigs.
Right. And just to contextualize that with some numbers, the public ones I found that everyone references are from this paper Slacker from 2016. And their number, I wrote these down because there's no way I could remember this. They claimed that 76% of the startup time for a container is in copying and installing stuff. Whereas to actually start up, you only need about 6% of the data and the image. So it's a pretty substantial amount, especially when you aren't doing stuff like we are, where you're trying to slim down your images as much as possible and have actually everything in that image is something you need. Most people don't do that. And so for most people, these kind of lazy file system things are super useful. I'll pause because in my life, this is where I have this cutoff point. So I obsessed with StarGZ a little bit for a while. There was a lot of efforts from people to switch from gzip to Z standard, which we could talk about. But let's get back to that later. My wife had a child with me in the interim. And so there was a point where I was just sitting around a lot, holding a baby or, not able to sleep and thinking about gzip and thinking about this stuff, because right before we had this child, I learned some things from someone on Twitter who kind of nerd sniped me into this. So I have this website I maintain for exploring container images because that's most of my job. And especially at work, people just ask me stuff. And so I was like, let me make a website for you that can answer your question. So I don't have to, and I can do other useful things. So the website is oci.dag.dev. And if you go there, you can put in a container image and it'll show you what that looks like. And you can click on the DAG links to layers, and then it'll load the layer and show you the contents. You can click on the files and it'll show you the actual file contents. So I made this. And then someone on Twitter made something very similar. So Aiden Steele made a very similar website. And I liked a lot of it, but I didn't like other parts of it. But the thing that I couldn't believe is how fast his website was to load file contents. Because in my mind, you would have to decompress the whole thing and store these files separately on a disk somewhere so that you could very quickly load them, because with the tar-gz, right, you have to seek through the entire thing until you find the file you want to use. And so I was like, I have to talk to you because I have to understand how you're doing this, because as far as I can tell, it's impossible. And so I got him on a Google Meet, and he showed me that you can do even more clever things with gzip if you drop down even further a layer into deflate. So there is a tool called, I think, gztool, and it allows you to get random access with a tar-gz file without modifying it, which is something that I thought was impossible. To the point that, like, when I learned how it worked, I couldn't stop thinking about it. And I even wrote a poem basically about deflate.
But you have to read this poem. Like, you have to, like, we need to hear it.
So I have an abridged version of it that I might share if I get very comfortable. But yeah, so I was reading like a lot of children's books, right, at the time, to a toddler, or I guess an infant.
I love that you did this while like not sleeping, because like if I told you the amount of times that I figured out code in the middle of the night or like while holding a sleeping child, it's a low-key flex, okay? Because when you have kids, you are forced to walk away from code sometimes when you're like trying to beat your head against it. And I used to think that made me a bad engineer until my kids went to go hang out with their dad for 2 weeks, and I was like almost less productive because I didn't know when to walk away. Right? Because I have all these breaks that are set in my day, like you got to pick up kids and do all that. And then it was just amazing. Like I sucked so bad because I'd sit there and try to like bang my head against the wall. I get the best, like I can write a doc in my head while holding a sleeping child. Like
there's something to it, right? Where you like,
yes,
you have no options. You are only in your mind. And so it's like, how can I?
And it stops you from writing code too fast. Like I was reading a book and it's like about thinking, like it's about doing technical, like mathematical and like technical things and how to like teach yourself like more efficiently. And there was a whole part about like, there were different like ways that famous people in history have learned how to teach themselves things. And one was like a guy swirling like ice in a glass. And then another one was like, you know, those balls that people like have that like back in the day that were like used for concentration, like squishy balls and all that kind of stuff. Like they talked about all these different ways, but it all came down to like, have you ever cleaned when you should be doing something, but instead you end up cleaning or doing something random, but it's something that's like mindless.
It's part of the process.
Yeah, it is a whole but this whole time you're like, I'm being unproductive, but you're not being unproductive. Yes. You're actually like, it's like hacking your mind. And I was like, oh my God.
Daniel Kahneman has a great book called Thinking Fast and Slow. And it's like, 15 years old now or something like that. But it's an amazing book on like, hey, when you're in the moment and you think of things quickly, like you have to take a step away and you have to just think slowly, not necessarily about the problem, but you have to think around the edges of the problem. And then ideas come back.
It's amazing. Like that's why people think of like fixing your code or whatever, like in the shower or like when you go to sleep, because your brain is working through it subconsciously.
Oh yeah, naps are my superpower for debugging things. Like You're
such an old man.
I've debugged so many things, like, but I was like, you know what? I can't think of the solution right now. I'm going to close my eyes for 15 minutes and I'm going to come back. And if I still don't have a solution, I'm going to go for a walk.
Dude, and I thought that was being unproductive. And then I learned how to go for a walk and like take a break. And I was like, no, I have to figure it out now. And you have to be like perfect. There's like my favorite TED Talk is learning how to be brave, not perfect. Shout out to like the lady who created Girls That Code. She like did that one. But it's so true. Like, see, Justin's been doing the secrets this whole time. And you were doing the secrets holding a baby. Like,
I think the only time I can solve problems is really when I'm not trying to, right?
It is so
you're
true.
Forced to sit with your own thoughts. And I'll share one more example of this. I went with some friends to, I don't know what it was, like Handel's Messiah, I think, a Christmas like play. I was just so bored because I like didn't understand what they were saying. It like wasn't English, or I just couldn't hear anything. And so we were just all sitting there like, this is not that pleasant. And so then my mind just started wandering to this stuff we're talking about actually. And I solved a problem I was having with my oci.dag.dev website. And I realized I could store things in a particular format to make it amenable to like seeking so I wouldn't have to buffer anything at all in memory. And I was like, oh, I've done it. I figured it out. And
I have to go.
I was like, I figured this out. She's like, I don't care. Like, okay.
Dude, I told my son that and I felt like the most old person ever. But I was like, sometimes you have to learn how to be bored. And I was like, oh God, like I sound like my parents. Like, you know, like I like telling people. But like, it's true though. I was like, you keep going from one thing to another. You don't ever let your brain sit and think.
Yeah.
And my brain is always going from one thing to another. So it's like to learn to just be like.
So you discovered Deflate, right, John?
Yeah, right. Back on track.
All the way baback to we're giving up on Star GZ. You had a kid, you discovered Deflate, and you're thinking of this stuff.
Yeah, wow, that's a great summary. Yes.
So I'm here.
This is why we keep Justin around.
So I want to try to describe Deflate to you. I think without a visual aid, it's basically impossible. But I've also on podcasts, like I think basically what we're describing, if I'm forced to try to visualize something just from hearing someone describe it, I actually have a way better chance of understanding it than if they give me like a really good visual diagram. Because I'm like actually flexing my mind trying to like grasp what they're saying.
It's like when you read a book and you have to imagine the scene and it's not a movie.
Yeah, exactly. So let me try to explain this. And if it doesn't make sense, that's fine. But so Deflate is essentially the body of gzip. If you were to look at a container image layer, I would attribute like maybe 16 bytes of it to gzip total, and then the rest of it is all Deflate. And so when you talk about gzip, what you're really saying is like a Deflate with a header that's gzip and a trailer that's gzip. And so the gzip parts of a gzip archive are just a header that says like optionally the file name. Definitely it says, hey, I'm gzip. And then there's some places to put metadata. And then the trailer is, hey, here's a checksum of all that data you just read and the size that you expect it to be. But because gzip's so old, the size is an int32, which means that it's actually size mod 2 to the 32. And so that's annoying for a lot of reasons. But yeah, the gzip part of gzip is actually very small. The Deflate part is the actual like, hey, here's how compression works part of a gzip archive. And it's based on something called LZ77, which is math, basically, that I don't understand. But the Deflate algorithm is something you can understand pretty easily. Deflate is made of a sequence of blocks. And it's kind of like a linked list where you just keep going through it until you find a block where there's a header that says, hey, I'm the last block. And so you read through a bunch of Deflate blocks and decode them individually, and then you stitch those contents together, right? So the header is just 3 bits of a Deflate block. A Deflate block starts with B final, which is a bit that's either 0 or 1. If it's 1, it means, hey, I'm the last block. When you finish reading this, you're done. Stop reading. And the next 2 bits are the type. So there are 3 types of Deflate blocks. There could be 4, but the 4th one is reserved and not used. So the first block is, hey, I am uncompressible data. The encoder just gave up because this data can't be compressed very easily, or you didn't give me enough time to like figure this out. And so that just starts off with a length that says, you know, I have 100,000 bytes and it's all like binary data. So just copy the next 100K bytes out of this block. That's great for like if your container image contains, say, like literal images like JPEGs, right? Those are also deflated and encoded already. So you're not going to be able to compress them any further. Okay. So that's B type 00, first one. The next block is fixed compressed, which means that it's a compressed block, but the Huffman tables are hard-coded. So what does that mean? So the compressed blocks have a header themselves, which is like 2 Huffman trees. If you're not familiar with Huffman encoding, I'm not going to try to explain it, but I'll do it very quickly. You can imagine that most data is not like uniformly distributed. So say you have some English text. If you think about ASCII, like there are 256 possible ASCII character bytes, right? English is not many of those. So if you just have a bunch of like text, you're going to want to prioritize like, say, the letter E over like 0 with space or something, right? And so what Huffman encoding does is it basically sorts all your data by frequency and then encodes them in a way where the most frequent things are small and the less frequent things are large. And so it's just a way to basically make a bunch of stuff smaller in a generic way that's very clever, right?
Oh, it's like a complicated tree, basically. But like
It's trees, yeah.
And roughly, like if it's a text file or a book, right? I could say like, hey, I see space THE space a lot, so I'm gonna just say that's in here the most, and so I'm just gonna say that's number one. And then anytime you see a number one, it means this, right?
Are we willing to be very pedantic? Because that's not quite right in the context of deflate.
Yeah, what? Why not?
Okay, so there are actually two trees that they themselves become Huffman encoded. So the start of a compressed block is a tree that contains two trees worth of data. One of those trees is for literals. And so each like byte is encoded as a Huffman encoded literal. So you have like 255 of these, right? Those are Huffman encoded, but it's just one character. Whereas what you're talking about is multiple bytes as a sequence that is repeated often, right? That's the second bit. So beyond just Huffman encoding, you also have, don't remember what the RFC calls them, but basically pointers. So it is a pair of bytes, maybe more than one byte, but it's two numbers essentially. And it says, hey, I'm a pointer. If you go back 12 bytes and then copy the next 4, that's it. That's all you need. So do that, please. And so with your example, you had THE space. That happens a lot. You're going to end up with this pair of numbers that represent the previous time you saw THE space. And so you just go back, you copy that, and then you keep going. And so it's those two things together that give gzip really good compression ratios. The other cute thing that I think I didn't realize before staring at RFC 1951 for a long time is that with those pointers, you can actually like predict the future. So let's say you have 1,000 zero characters, which happens at the end of a tar stream. So this is a real thing. You can say, hey, go back one character, that's a 0, and then copy the next 1,000. And it knows like, okay, the next character will be a 0 after I copy the first one. And so it can just like kind of predict that. So you can get, if you had like ABC, 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 you can say go back 3 and then copy that for the next 9. So there's this cute little trick that allows you to get long spans of like padding down. I kind of lied a little bit. You can't do 1,000. I think the maximum length is like 100 something or 200 something, 263 or something. But it's a good technique, right? So popping the stack a little bit. So the other type of blocks are compressed. So we have compressed blocks. With B-type 01, these are fixed trees, basically. So they're hard-coded like in the spec, and you don't put them in the block themselves. They're out of band and everyone knows them. And so this is useful for compressing like really small data where it's not something you want to like encode an entire Huffman tree in, because that's going to end up being bigger than the data itself. So like if you were to compress like, hello, my name is John, it would end up being B-type 01 and it would be fairly small.
why is it immutable though? Like what makes that?
It's just like a little optimization. Like, so deflate itself is a cute engineering trade-off of a lot of things that are aspects of like LZ77. But it's just an optimization where if you have a small amount of data to encode, it's better if we all just agree ahead of time on like what those trees would be, so that we don't have to put it in the data stream. It's just part of the algorithm.
It's just hard coded in the spec, right? You're like, hey, we're going to do this type of data. And if you're decoding this type of file, if I reference it, I don't need to add it myself.
Exactly. The last block type is compressed dynamic, where at the start of the deflate block, you have this inline encoding of the Huffman trees, where you have the literals encoded and the lengths encoded. And that's it, actually. So that's all of deflate, right? So writing an encoder, very complicated and like a lot of magic and wizardry and stuff. But to decode, it's actually like kind of straightforward. Y'all seem to understand that, right? So now, ta-da! You've learned how deflate works. The magic trick, now that you understand deflate, is turning that into a seekable tar-gz stream.
And not seekable as what star-gz was doing with those blocks of metadata.
Exactly.
Now you can go right to the deflate block and pull out the smaller blocks in there and know how to decode just those bits, right?
Right.
So are you then like almost indexing deflate?
Yes. So I'll describe this algorithm. It's very cute. And then maybe we can do the
You're
poem.
the only person that makes things cute. Like, I'm loving this. Like, we just made compression cute. Like, this is amazing, and I'm so here for it.
So it's so clever, right? Like I can't believe it. So the last piece of information that you have to understand for this to make sense is with those pointers, right? When you're seeking backwards to copy some data you already saw, there's a limit to how far back you can go. And that's very, very important for this. So because like gzip is, circa early 90s, how far back you can seek to copy some data is limited by the computers of the time and the amount of memory we have available to us. And so a reasonable number was chosen that was 32 kilobytes. And so you can only reference data that's within the last 32K that you read so that it can be like hot in memory, right? It's fast to decode that. What that means is that if I have that 32K around somewhere, I can give it to the decoder if it asks for it. So the trick of this seekable deflate stuff, and if you want a good implementation of it, Amazon actually put out something called the Sochi Snapshotter, which is seekable OCI. So Sochi Snapshotter is like this trick applied to container images. What you do is every so often, when you're decoding this gzip stream, similarly to how StarGZ works, you would just cut off the gzip stream and restart a new one. Instead of doing that, you take a little checkpoint. So you hit like a deflate block and you say, hey, I'm going to just save off to the side the previous 32 kilobytes I just read of uncompressed data. And I'm going to do this every, say, like 4 megabytes. And if you do that, then you can also seek to that point in the future and start decoding from there.
So you're making your index as you deflate it.
Yes. And notably, you don't have to change the input at all.
Does that also help if, like, say your download got interrupted, you could then start at those same intervals?
Yes. You could also do that with, yes.
Would that help for like data recovery also? Like, say stuff got interrupted and for when you need to learn when to start later, if you do get interrupted?
Yes. So it kind of depends on how you do that. Like if you download the whole thing first and then unzip it, then yes, you don't need this. But let's say you're downloading the whole thing, and as you're downloading it, you're like unzipping it and writing it somewhere, and you're not keeping track of like any of the previous stuff you downloaded. You could use this technique to like restart from more recently than the very beginning. So yeah, I mean, this could work as a way to restart a download, which is clever. I haven't done that, but yeah. So the other thing you need for this to work is the table of contents of like, okay, I have a tar file. I need to know where in the stream that offset is. And so you end up with this index of checkpoints, which tells you how far into the gzip stream you can seek, both like the compressed and uncompressed offsets. And then you have this table of contents for the tar file that's the uncompressed offsets for each file. And then you do effectively a join of those and say, if I want this tar file, I need to seek like 30 megs in. Let me find the closest checkpoint I made to that 30 megs in. Oh, there's one at like 28 megs. Cool. I will seek to that 28 meg point and then start discarding until I reach the tar file. That lets you skip the first 28 megs entirely and only download, that slice of the gzip that you actually need. So that's the trick. That's how Sochi works. That's how my container image website viewer thing works. And it's really fast, right? I'm in love with it, right?
And at that point, for something like a container image, you don't have to package it a special way. You have to build an index of the package contents.
Exactly. And this gets into some OCI stuff, but where do you store those was kind of a question that people had for a long time. And there wasn't really a good way with OCI to associate one artifact with another without like just rebuilding the thing. We kind of hacked around this. I was once responsible for cosign. That's another one. So the way that cosign works is you have like a specially formed tag in the container registry that gives you that edge from like, hey, this is metadata about this image, and I'm going to push it to this magical tag name. In OCI, kind of recently, we standardized like 1.1, which adds a field that lets you associate like one artifact with another artifact. And so what the Sochi folks do is they use that and they say they push to the registry the Sochi index, which has all this information and associates that index with the container image that it's referencing. So as a client, if you're like, hey, I want to access this lazily, you can ask the registry, give me all the metadata that references like this image. And if one of those things happens to be a Sochi index, then ta-da, like you can lazily access it without modifying it, which is the whole trick, right? It's like we want to do this without actually touching customer images or images we built from some other way.
Right. And you don't want to force people to rebuild everything with a special tool that isn't globally supported maybe, or they don't use it everywhere. So then you're like, oh, I have this one version of the image that is compressed in this certain way and another version that's like just straight Docker. It's like, oh, well, but if I'm pulling it, will my tools know how to do that? Will my Kubernetes cluster get the right thing? And instead you could say, oh, it's an extra metadata thing. If someone ignores it, that's fine. They'll download the whole image. It's still a standard OCI image with all of the normal stuff you'd expect. But if they do support that metadata and say, oh, I can download this faster, there's a separate piece of metadata attached to this image, and I can go and fetch that piece, which is much, much smaller, and then seek through the image for the files that I want in an order I want them, or however I'm associating. Like I just want the startup bits for that first.
Exactly. And the crucial bit for me is that I can use this technique on all existing container images that have ever been built, and it works. And so that's great, because for my purposes, I want you to be able to look at any image quickly, and you can. The size of the index ends up being, it depends, but heuristically, like if you decide every 4 megabytes, I'm going to take a checkpoint, then it works out to be about 1% the size of the original archive, because you're paying for 32 kilobytes for every 4 megs. For really big images, that 1% actually ends up being big still. And so the clever thing I did, I think, as a contribution to this like whole idea is that my index format I made also a tar gz file. And so if I decide that index is too big for me to hold in memory, I re-index it. And so that thing itself is indexed. So if your image is like over, I think 20 gigabytes, then I'll end up creating a secondary level of indexes so that I can lazily access my index to lazily access your image. And because you get like 100x every time you do that, it ends up, I think you only ever need 2 levels, because most object stores only let you store like a 5 terabyte image or something.
Right. But even like a 5 terabyte, you shrink that to 1% for your index, and then shrink that to 1% again for your index of index. And you you are not downloading a 5 terabyte image to get the files you need.
Yeah, this was my eureka moment during the symphony. I was like, oh, I know what to do.
And that applies beyond just containers. I mean, you're obviously doing it with containers now, but even for things when I think of like large language models, like if we are compressing those and we want to like decompress pieces of them, or if we only want to get like some portion of any large file that's in a tar, this indexing applies.
Yeah. And in fact, something that's interesting about that is that certain projects store their large language models as OCI things. So like the Olama stuff, you can look at it using my tools because they're just in a registry somewhere. The other application of this, as we talked about at the beginning, is that APKs are 3 gzip tarbells in a trench coat. And I also made apk.dag.dev because I was tired of debugging our packages. And I was like, wait a minute, these are just gzip tarballs. And so I forked it a little bit and just changed a couple things. And I was like, great, all this technique now works for all our APKs. I was very proud of that. It's great.
It should be.
Yeah, that's awesome.
Anything that makes debugging easier, all for
and
it.
faster, right? It's like the same thing with like when you're marshalling and unmarshalling JSON, like hey, what if we could speed up how fast this disk is and just get past the problem by making that as extremely fast as possible. And in this case, we're like, hey, what if we can get beyond I have to download this big thing by saying, I only want to download these bits. And right, you could like throw away or ignore all the rest of it and just say like, I just want this piece. And
I feel like those are the hardest parts too. Like those are the things that you spend the most time on, like debugging and trying to find things. If you can make that easier, you've already cut a lot of your engineering hours.
Yeah. But what I do now is if I'm ever doing something where I'm just twiddling my thumbs waiting on something really slow, it's like, I should spend this time making it not slow. And so anytime I'm waiting on CI or whatever for something, I'm like, let's whip the profiler out and actually see what's going on. That's what led to all this, basically.
Well, John, thank you so much for coming on and telling us all about RFC 1951 and how deflates and gzips work, because that's just awesome. Like I love all the nitty gritty in that, of like how broadly that applies and how specifically it allows things like your DAG to work and to be performant and to let people have those tools.
Can we get the poem though? Like we need the poem.
Oh, that's a plus thing, right? Is that
it could be. We could put a teaser in, because so no joke, it's like a 10-minute read.
Dang, you wrote a poem. Like,
yeah, I'm kind of embarrassed. Maybe it should be. I think maybe it should be plus subscriber content, but
that's fine. Yeah, if you are a plus subscriber and you want to hear the poem, John can read it out for us if you're feeling comfortable.
Yeah, well, I feel like I kind of owe it to you because I spoiled.
You did tease it,
Jason's episode. So. You know, let me take a sip of water because it's gonna go.
I'm really excited about this.
What's up, friends? Do you remember when ChatGPT launched? I do. It felt like the LLM was this magical tool out of the box. However, the more you use it, the more you realize that's just not the case. The technology is brilliant, don't get me wrong, but it's prone to issues like hallucination on its own, but there's hope. There is still hope. Feed the LLM reliable current data, ground it in the right data and context, then and only then can it make the right connections and give the right answers. The team at Neo4j has been exploring how to get results by pairing LLMs with knowledge graphs and vector search. Check out their podcast episode about LLMs and knowledge graphs throughout 2023 at graphstuff.fm. They share tips on retrieval methods, prompt engineering, and so much more. Don't miss it. Find a link in our show notes. Yes, check it out. Graphstuff.fm, episode 23.
Thank you so much, John, for coming on and sharing everything about TARs and deflates and all the things that I learned through this. It was fantastic. And I love, I knew about John's container websites before to explore layers and containers.
I want to go back and listen to it so I can when you're just like, this is so cool, but I can't process all of it. Like I need to listen to it 3 more times and then draw some pictures and stuff and then go check to his website and I'm going to know all the things about TARs.
Yeah. Getting hands-on with some of the tools would definitely help.
Yeah.
But for the outro today, I have it's a weird, not necessarily a story, but a history lesson maybe, because something that we were talking about in the interview reminded me of something that I read in a book. And this book was called A Mind at Play. And it was about Claude Shannon. And Claude Shannon was someone who lived in the 20s through 60s time frame, or at least that's when they were active in work. And one of the things that I remember was he basically created how we transmit data and how we're able to transmit data in technology in general. And one of the cool things about it was he was working on checksums for how do you verify that information is the same? And how do you just say hey, when I send this information, I can validate that I sent you the right thing. And the cool thing about it was he associated that compression, when you compress something, you're finding the patterns and you're taking them out. When you're encrypting something, you're doing the opposite of compression. You're removing all the patterns and you're making sure that no patterns exist. And so you cannot.
That is super interesting.
It was really when I read that, I'm like, oh my gosh, that is the simplest way that I can think about compressing something and encrypting something, where encrypting, you're making noise out of structure, and compression, you're trying to take out all of that structure and make sure that it repeats itself over and over again.
I just had a whole epiphany about encryption. To give context, okay, this is how me and Justin's relationship goes. I get really excited about something and then I text it to him and then he's like, I read this book, and then he tells me about it. And at some point, both of our eyes light up and we get really excited, or we get really into it, and it's great. You just to be Justin's friend and for him to be like, I just randomly read this, and it's a whole roller coaster. Highly recommend it. But that is really interesting.
Right. Compression and encryption are just opposites of each other. And so let me walk through just a couple of his major things that he did in his life because he was such a fascinating person. In the book, A Mind at Play was really good because it starts out as basically like
Do you read audiobooks or do
I
you
do
actually
audiobooks,
read
yeah.
this? Okay.
I do audiobooks. I can't sit down and look at words to consume the words. I consume them with my ears, not my eyes.
That's good that you know how you learn. That's really important in learning.
He was a very eccentric person in a lot of ways, where he was a master unicyclist. He was a great juggler, and he also would have trumpets that would blow fire. He had all these like toys and things that he would like to play with and explore and do. And he worked at Bell Labs, and he was kind of known as like more of a silly kind of extrovert person.
Okay, low key though, is this not the best buy-in for neurospicy people? Like, for one, me and you are here. Like, hello. Like, and this dude, looking at the stories about Steve Jobs, like, it's so funny. Like, from hyperfixation food to just like wearing one thing over and over and over again because it, like, your brain doesn't have to do the work of thinking about what you're gonna wear, you know?
Right.
And then you think about how many people in tech would just wear a t-shirt, just wear a sweatshirt, you know what I mean? And how many people just got straight black shirts or like regular socks or whatever, you know what I mean?
Yeah.
It's just so funny. Like, we're talking about patterns, but there's also so many patterns of this that you see in like people that work in this industry. And like, it's just, I don't know. I feel like all the patterns. Like, and it's always like these really like eccentric or like different people. They have like the coolest minds. Like, my son has autism, and I always tell him like, I'm like, you don't need to be the same as everyone else. You're going to be like so cool because your brain works differently, you know?
In 1937, Claude Shannon has his master thesis, and it is described as the most important master thesis ever written.
Shut up.
In this master thesis, he describes how you can take a switch and make Boolean logic circuits with
Sounds like a freaking
switches.
genius.
He basically invented, like, this is before transistors. This is before they knew how to make like AND gates and OR gates. Like, he described it, and he said like, oh, you can solve logic puzzles with just true and false, just ones and zeros with these logic gates. And this was in his master's thesis at 21. And he's just like, yeah, like, this is how you would do these things, and this is how you can solve this. And 37, again, this is 1937, before computers were like a thing.
This is why I think like real revolutionary like moments in tech or technology or industry or whatever happen in simplicity that is like timeless. Like, look at between him, Ada Lovelace, that was a time when we didn't have anything close to computers, right?
Yeah.
But they were already thinking in a way that is still completely valid. I use checksums all the time
Right.
in engineering, you know what I mean? So just think about how that not only withstood the test of time, but is still like completely like you can implement it today. And that just shows you like when it's really a thing that is like groundbreaking, it lives forever.
Yeah. And that was for Claude. It was about 11 years later. He had a paper called A Mathematical Theory of Communication. And that is literally where he like lays out like what checksums are.
That's
Like, people
amazing.
like, how would you communicate two things over a wire? And he's like, mathematically, this is how we can prove how this would work. And it was known as the Magna Carta of the information age, like the very beginning of we can send data to someone else and verify those things. And this is also like, he was working as a cryptographer in World War II. And he has still to this day, the Vernum cipher is what it's called. And it's to this day, the strongest cipher that exists that cannot be broken.
Which is wild because so many ciphers have like
Right.
been, you know what I mean? And just the fact that like encryption libraries have had to advance so much to keep up with it. Nowadays, like, people don't even really want you to write your own like encryption because it's so easy to break them, you know?
Right. And so he was proving that, again, this is without computers, like mathematically, how could we like essentially encrypt something? How do we add noise to structure and then send it to someone and then make sure that they can get the same message out? And there's a really cool, if you go look up that cipher, the Vernum cipher, there's a Python script that's like not even 50 lines. And you can just see like you can actually like follow it. Like, okay, this is where this changes and this is how this changes. And I was like, that's fascinating because it's so simple, but he proved it with the math to say like, this is how you would make sure that
The best stuff is simple though. Like the best
Yeah.
stuff in fashion and design, technology, it's always simple because it's really got the value there and it doesn't need a bunch of other stuff to like prop it up.
And then the last thing I was going to point out that he did was in the 50s, he was the first person doing machine learning back in the 50s. He had this mechanical mouse that he would train how to solve mazes. And he had one of the very first computer human interfaces for playing chess or it was a chess-like game. I don't think it was actually chess, but he was basically, it's like, he has pictures of him with this big box of circuits that was like playing, and you could like move the pieces and it would light up like where it would want to move the pieces. So you're playing chess with a computer back in the 50s. And that was the very first time. And he was like, how do we learn how this stuff works? And so it was super fascinating. Like his life was incredible. And so A Mind at Play was a really good book. But also there's a documentary that I rented. I'm going to watch it.
Will you send it to me?
Yeah, I'll send it to you. It's called The Bit Player. And so you can rent it. I think it's only on Amazon. That's the only place I found it, but it's a documentary about it.
Do you ever read about these people and wish that like they were still alive so you can meet them in real life? Like some of these, like Albert Einstein and like this guy and like Grace Hopper, just some people you're just like, dude, they were probably so fun and eccentric, but like brilliant, you know?
Yeah.
If there's one person from history that you could meet in real life, who would it be?
Oof, that's too hard.
Like an inventor or like someone like that.
I mean, I would love to meet Tesla. I've read so many books about him.
He got screwed by Edison hard too.
Oh man, he was a horrible
Like,
business person, right? Like he was
you
not the
imagine-
business person.
because he was so creative, and
Yeah.
Edison was a better business person, but
Yeah.
kind of a douche. Like,
And a lot of these lives, it's really unfortunate to hear how they don't see the outcome of what they invented and what they did.
that's like a major correlation between art and technology too, because look at like a lot of times it's like they're using it to work through other problems also, like look at Van Gogh and Monet, and like people were like their art's terrible, impressionism's horrible, and you're like, dude, he's gonna be one of the most prolific, like he started his own like movement almost, you know, like, and he's gonna
Yeah.
be one of the most prolific artists.
Those are all like kind of tragedies where like even you think of like Ada Lovelace, right? Like she was like alone and on laudanum for the like ending of her life. And,
Yes.
like all of these things happen that's just like, oh
Mary Carey,
yeah.
literally, like they killed themselves in like for science, and we wouldn't have X-rays without them.
Right.
That's amazing.
Yeah.
It's my kid's favorite scientist.
There's a lot, but for Claude, I actually don't remember how he ended up passing away, but
Einstein had kind of a happy life, sort of, but the first part of it was sad. They like called him all kinds of names and thought he was like not that bright when he was a freaking genius. He actually got a D in physics, which is like hilarious because now they're like teaching the theory of relativity.
So anyway, I just wanted to go over that because again, this interview reminded me of the book, and his life was pretty remarkable in everything that's.
I'm gonna go look him up. I want to know how his life went.
Yeah, the book is good. I'm going to see I'll watch the documentary, and I'll send it your way too. It'll be in the show notes for the podcast.
I love the like rabbit holes that we go down of like interesting things. I can't believe we get to do this on the podcast. It's awesome.
I particularly love like his like technical history.
I love history.
Partially because I was born in the 80s, but I never had a computer until the 2000s, and so I feel like I missed out on like a golden era of like the internet
same.
and computing. And so like there's a lot of it that like I try to relive through books and like figure out like what happened in the like 50s through the 90s where I was not involved at all with technology.
But it's so crazy that so many like major breakthroughs happened before computers were ever really a thing, if you think about it.
They all led up to it, right? Like it was like, hey, this isn't all these things that are new in the last 20 to 30 years have at least 100 years of lineage of like where people started doing it.
Which is funny because I wonder what else you could learn from history to like create the new like influential computer breakthrough. Now that we got super philosophical.
Thanks everyone for listening to the show. When this episode comes out, I actually am going to be at a couple conferences in June. So if anyone's out there and going to conferences, I will be at SRE Day in San Francisco and Cloud Native Security Day in Seattle. So
we're going to have so much fun. We have to hit up all the donut spots. We got to go to coffee spots. We got to like, we're getting all the food. It's going to be so much fun.
But if anyone's at those conferences and wants to meet up, feel free to reach out. I'm available online and I'll hopefully see you around. But
you're going to sneak me into the security one, like in your backpack, right?
Sure. Yeah. I got a big luggage bag. We'll just carry you right in. So,
we can get a surf bag. Like, it'll be awesome.
So thanks everyone for listening, and we'll talk to you again soon.
3, 2, 1.
Thanks for listening to Ship It with Justin Garrison and Autumn Nash. Subscribe now if you haven't already. Head to shipit.show for all the ways, or just search for Ship It wherever you get your podcasts. You'll find us. Thanks once again to our partners at Fly.io, to The Mysterious, Breakmaster Cylinder for these dope beats, and to Sentry. Use code CHANGELOG when you sign up and save $100 off their team plan. That's all for now, but come back next week when we continue discussing everything that happens after Git Push.